All right, so we're gonna do this again. So this is problem set 3, and it's a bit more complicated than last time, but not too much. So let's jump right on into it. So for number 1, we've got this limit of this function here as x approaches 49. And once again, if we have lost that clear picture of what a limit is, let's say x equals 49 about here. As my function gets closer and closer to where x equals 49, so as it gets closer from this side and as it gets closer from this side, I'm looking for what point this is going to be. Obviously, I just drew a random function. This isn't actually what happens to be right in there necessarily, but I'm not actually looking for what this point is, just what the function is approaching, right? So in this case, it happens to be approaching what the point is. But if, for example, I had maybe this function, except I have a big hole in it, maybe not that big of a hole, like a big hole right here. Like there's no point there, it's undefined. If I plugged in something from my equation, I would get an undefined answer. There's nothing there. So I have to pay attention to the points around it that show me what we're getting close to. That's what our limit is. On that note, we do typically like to just start off with direct substitution, as I did for a lot of problems in the last video, which is where we just take this value and we plug it into our function. Because a lot of the time, the value at that point is going to be our limit. That's just not always the case, so we do want to be careful about that. But a lot of the time, that is the case. So we're going to try that now. We always like to try substituting first. So I'm going to just plug in this 49 wherever I see an x. So this is going to turn into the square root of 49 times 49 minus 45 squared. And obviously 49 minus 45 is just going to turn into a 4. And the square root of 49 is 7. So this turns into a 7 times 4 squared. 4 squared being 16. So it's 7 times 16. Whatever that multiplies out to is our limit. And let's see. I think that's 70 plus 42. So that'll be 112, I believe. It could be wrong, but I believe that's correct. And so luckily for us, direct substitution worked there. We're going to try that again for number 2 and hope that we get an answer. So we're going to plug in this 0 this time because we're looking for around that point. So just plugging in a 0 wherever I see my x, as you do. So this turns into a 7 plus a 0 because the square root of 0 is 0. So it's a 0 times a 2, which is just 0. It says, again, 0 times an 8, which is just 0, over negative 14, which is just 7 over negative 14, or negative 1/2. Awesome. And luckily, once again, direct substitution worked for us. Remember, it's not always going to. And if we get an answer that has a 0 over 0, that's what we call our indeterminate form, which means we cannot tell from that whether or not there is a limit or what that might be. So when we get this indeterminate form, that's when we want to try something other than substituting. But again, if I get something, like if I get 0 over 1, my limit is just 0. If I get 1 over 0, that's undefined. So we don't have a limit there. That means our limit does not exist. Let's try this next one. Again, we're just going to directly substitute that in. So we've got this 3 pi over 2, and we're going to plug that in wherever we see an x. So that turns into a 2 times 3 pi over 2 squared times sine of, 3 pi over 2 over 3. And I could rewrite that 3 pi over 2 over 3. I could rewrite that as a 3 pi over 2. I could rewrite that as a 3 pi over 2 times a 1/3, right? Because that's the same thing that's happening there. In which case these 3's are just going to cancel out, and I'm left with a pi over 2. So I'm going to erase that bit now because it's in the way. And so this turns into a 2 times my 3 pi over 2 squared times sine of pi over 2. And we're going to square that 3 pi over 2, which is just going to be 3 pi over 2 times 3 pi over 2, which will be a 9 pi squared over 4. And then, so that's going to be what goes in right there. And since we're multiplying that by a 2, I'm going to get a 9 pi over 4 times 2. And I can kind of cancel these out so I get a 2 in the bottom now, right? Because this 2 over 4 is going to turn into a 1/2. So we get, oops, there we go. We get a 9 pi squared over 2 times sine of pi over 2, which is just 1, right? Because sine of pi over 2, if we look at our unit circle, we've got 0 or 2 pi, pi over 2, and 3 pi over 2. And obviously there's more points on our unit circle, but we're just going to focus on these. Remember that sine is our y value on our unit circle, and our cosine is our x coordinate. So at this point, here I've got a 0, I've got a 1, 0, because my x coordinate, my x is 1 unit over, and my y is a 0. But then at pi over 2, it's the exact opposite. My x is 0, because it's right there at that origin, and my y is 1 unit up. So remember, sine of pi over 2 is 1, so our limit in this case just happens to be this right here. All right, and luckily once again that direct substitution worked for us. So let's go ahead on to number 4. As I said before, we always want to start out with direct substitution just to see if it works. Because if it does work and we try something different, there's a very good chance that we're going to end up messing up the problem and getting the wrong answer just because we've overcomplicated it. So to start off, we're just going to plug in that 0. Oops. I'm going to plug in that 0. So I get this times this. And I'm actually going to erase that previous bit because it is a little bit in our way, unfortunately. Let me write the answer up there, though. Oops. 9 pi squared over 2, I believe it was. Okay, so now we continue. We're going to just simplify, continue combining like terms, what have you. So obviously e to the 12 times 0. 12 times 0 is just 0, so that's e is 0. Times, and I've got 4 plus 0 squared, which is just 0, so just 4. So then this reduces to a 1 times 4. Remember, because anything to the power of 0 equals 1. I believe we discussed that in the last video, but I am happy to go over that if anybody asks me to. But yeah, so our limit for this one just happens to be 4, and that works out pretty happily. Now this next one that we're going to do is a little bit more complicated. Alright, so what we're going to do for this one is we need to first recognize a very important rule, and it's something that we're just going to have to memorize, unfortunately, because there's no real good way to figure it out without much stronger and deeper math knowledge than we have time for today. So what's going to be very important for us to know, and you'll see that it tells us this in the textbook, it's something that we just want to memorize, is that the limit as x approaches 0 of sine of x over x equals 1. And that's always going to be the case. So yeah, the limit of this function as x gets closer and closer to 0 is going to equal 1. So we then see that applied in a lot of different places throughout math. So we can apply, we've got the same limit, and then maybe I have a sine of 2x over x. Well, this is going to be a 2 divided by a 1, so this just happens to be 2. It's going to be our answer. If I have a limit of x approaches 0, sine of x over maybe 3x, our answer is going to be 1/3, because I've got this 1x divided by this 3x here. And obviously that's not exactly what's happening. It's not necessarily an x divided by an x, but that's essentially how we're going to look at it for right now, just because the nitty-gritty of that is a little overly complex. It's a little over my head even. So let's go in based on that, and I see that we've got this sine of 6x over x here. Oops, it won't undo. That's no. Okay, well, that's unpleasant because it went into the other. There we go. So we've got the sine of 6x over x, which I know is going to equal 1. And then I know it's going to equal 6 in this case because of that 6x. And then I know that if I plug in this 0 to my cosine of 4x, that's going to be cosine of 4 times 0, or just cosine of 0, which we know is equal to 1. So this whole limit here just ends up equaling 1 times 1, or just 1. Oh, sorry, 6 times 1, or just 6. Because remember, we've got that sine of 6x over x. Awesome. Okay, let's go ahead and move on to our next one. I know that last one was pretty confusing. I hope that I explained it decently. Yeah, so we're going to move on to this next one, which is that much more difficult. Actually, this is probably the most difficult problem on the page. And so the first thing that I'm going to do is I'm going to go ahead and factor out those 5s that I see there. So I'm going to do the limit as x approaches 0 of 5 times e to the 2x minus 1 over 9 of x. And then I've got a really important thing to remember, which is another thing that we're just going to have to memorize, very similar to our limit of the sine of x over x, is going to be this term right here, which again has a very convoluted kind of nitty-gritty details to how this makes sense, but this limit is also always going to be equal to 1. And so what we're going to do here is we're going to manipulate this limit to be basically in this form. So I'm going to rewrite this as 5 over 9 times the limit of what's left. We've got that e to the 2x minus 1 over x. And it's almost in that form now, isn't it? Except we've got a 2x up here. And for anybody confused as to how I took this out, that's one of our limit rules, or our laws of limits. Because this is just a coefficient, you can pull it out in front of the limit rather than having it inside. So I pulled it out in front. So now I've just got this bit here. And so what I'm going to do to get us closer to the form we want, I'm just going to multiply everything by 2 over 2. And the reason I'm doing that is because I want this down here to be a 2x so that it's in that form up there, so that 2x equals our x, or I guess we could use another variable to denote that. So let's say, actually, let me rewrite this piece. Instead of using x's, I'll use u's. So if I've got this right here, if I put it in this form, our u is going to be 2x, which means it will be in this form, and that means that it will just equal 1. That being said, we haven't done that bit yet, so I'm going to erase that. So we're multiplying by this 2 over 2, which is doable because 2 divided by 2 is obviously 1. So we're not actually changing the value, we're just kind of manipulating our function here. which gets me 5/9 times the limit as x approaches 0 of 2e to the 2x minus 2, obviously, over 2x. And again, I'm going to factor out what's in that top part there and put it in front of our limit. So we're going to go ahead and rewrite that again. And I'm going to skip that little step because I'm factoring out this 2 and then putting it in front. So it's going to turn into 10/9 times the limit as x approaches 0 of e to the 2x minus 1 over 2x. We see now that this is very much in that same form, which means that this limit equals our coefficient times 1, or just 10/9. And that was very complicated. Luckily, the rest of the problems are not nearly as tricky. So let's go ahead and move on to number 7. If you need to go over that last one, feel free to pause, rewind, what have you. Again, Google is your friend. Yeah, so let's go ahead and try this next one, and we'll see what happens when we plug in that 0. So again, we get 0 on the denominator, which tells us we're already in a bad spot. But now we need to check if we get 0 in the numerator, which we will, because that will be sine of 0, which is just 0. So we get a 0 over 0 here, which means we can't just substitute it in. But what I notice about this is that it's kind of in that form of our sine of x over x, which we mentioned just a few minutes ago, that as x approaches 0, the limit of sine of x over x is always going to equal 1. And as I discussed right with that, if I have something inside of here, and maybe out here as well, we're just going to kind of divide those together. We're going to just treat it like that. So in the case that we have here, oops. Uh-oh. Goodness. I don't know why I did that. So in the case we have here, we've got a sine with a 3x squared over a 4x squared. So that's just going to be 3/4. But we've got a 9 in the front. So it's going to be 9 times 3/4, or 27/4, which we can obviously rewrite as, I believe, 6 3/4. And that's our answer there. All right, now we've got some more laws of limits going on here, some more limit rules, things that we have to memorize, unfortunately. So for number 8, we've got this function here. And the first thing that I'm going to do is I'm going to not rewrite it. I'm going to recognize another law of limits, another piece that we need to memorize, that again is in our textbook, and it's just something we want to remember. So what we're going to find is that cosine of x minus 1 over x, the limit of this, is always going to equal, I believe, 0. Yeah, so that's always going to equal 0. So what we can do here is we can manipulate this to realize that we have exactly that, right? Because I can factor out that 2. So it's just, oops, I forgot my limit, sorry. So the limit as x approaches 0 of, and I factor out my 2 over 3x to the 4th. And so this bit right here is in that form. And so I know that this is all going to equal 0 times 2/3, but obviously 2/3 times 0 is just 0. So our limit is 0. All right. Now a little bit of a less tricky one, thank God. Less laws of limits and just kind of factoring rules here. So we've got the limit of this function here as x approaches -16. And so I'm going to rewrite that. I have x approaches -16. The first thing I notice is that we have two denominators that are the same here. When we have two denominators that are the same, obviously we can combine those fractions because they have common denominators. So I'm going to combine them. I'm going to turn it to an x squared minus 256 over x plus 16. Oops. X plus 16. Okay. And now I notice that this is a perfect difference of squares. So I'm going to factor that out. That's going to factor out, in this case, to be an x plus a 16 times an x minus a 16, right? Because I see 256 is just 16 squared, and because there's that minus there, I know that I'm going to have these. And that's all over that x plus 16, which I can see cancels out, which is lucky for us because that means we no longer end up with a 0 in the denominator because now our limit is just this, in which case we can plug in that negative 16 and it turns into a negative 16 minus 16 or a negative 32. All right, just a few more problems to go, 7 more. Oops, sorry, 8 more, technically. Let's look at this one now. We notice that if I plug in that 6 in the denominator, I get a 0, and if I were to plug in my 6 up here, I would also get a 0. So let's see if we can do anything here. So I'm going to write my limit. And let's see. Well, I can definitely factor out this 5, so I think I'm going to do that. I'm going to try factoring out my 5, and I think that 5 times 36 is going to be 180. So this is what we get now. And these almost look like we can factor them out of each other. They're really, really close. So let's keep going, see if we can manipulate them a little bit more to do what we want them to. So I've got a 5, and I'm going to factor this out. That's going to be it's another perfect difference of squares, so it's going to be 6 minus x times a 6 plus x all over our x minus 6. And these are really, really close to each other now, aren't they? But they're not quite there yet, so we do need to switch it around just one more time. And so now I'm going to factor out a negative. Let's say, so I'll put it in front of my 5. I'm factoring out a negative, which is going to turn oh, wait, does that work? Yes. It's going to turn this 6 negative and this x positive, so it'll be a negative 6 plus x, or be written an x minus 6, still times that 6 plus x, or I suppose I could rewrite that, all over x minus 6, which now cancels, lucky us. We move on to the limit as x approaches 6 of just x plus 6, which is 12, if we just plug that in right there. Okay. Next one, and these are absolute value, in case that's unclear, and this is a 12. So in this case, we have the limit of this function as x approaches 12 from the left. That's what this little minus symbol is. It tells us that we are looking for the limit from the left. And the reason that's important is because our limit doesn't always exist if we're looking for the limit altogether. But if we're looking for it for just one side, sometimes it will. Or rather, the one-sided limit exists. So let's see. If we're just going to plug in that 12 to this, that's just going to get us, let's see, 2 times 12 is 24, minus 24, and then, oh, sorry, that's not supposed to be an x. That's supposed to just be 12 minus x. I miswrote that. Sorry. Oh my god, I did it again. 12 minus x, goodness. So that's a 12 minus 12, which just gets us 0 over 0. So that's no good. So what we're going to do instead is there isn't really much way to manipulate this one. So what we're going to try instead, obviously we can try to manipulate it a little bit, but a really easy method for finding our one-sided limit, just to be absolutely sure we're getting the right thing, is to quite literally just plug in values that are near that point. Because remember, a limit is just whatever y value I'm approaching as I get closer and closer to it from each side. So if I want the limit from the left side, I'm going to come in like this, which means I need to start with values smaller than 12. So let's start at maybe 9. We'll do 9, 10, 11, and 12 is obviously undefined. And let's go ahead, let's see what happens when I plug in my 9. If I plug in my 9, that's going to be an absolute value of 2 times 9 is 18, minus 24, then over 12 minus 9, which is going to equal, let's see, that's going to be a negative 6, because absolute value, 3, which is a 2. Okay. The next bit, we're going to plug in our 10, so I get absolute value. That's going to be a 20 minus 24 over 12 minus 10, which gets us 4 over 2, or just 2. Interesting. And now we'll plug in our 11. I've got the absolute value of 22 minus 24 over 12 minus 11, which is just 2 over 1, or just 2. The really interesting thing about this one is that it just happens to all be at the same point, but that gives us a pretty clear limit, right? That means that approaching from the left, we've just got this straight line. And maybe when x equals 12, it suddenly jumps up here, or maybe it goes down there. We don't know, right? But it doesn't matter because we're just approaching from the left. And so in this case, that shows us that as we get closer and closer to 12, our y value approaches 2. So our limit is 2. All right, let's try our next one. This time, we've got a radical. So we've got a square root. And this time it wants the limit of this function as x approaches 3 from the left. And so we see that when we plug in that 3, we're going to get this right here. We're going to get the square root of 0, which is just 0. And that very well could be our limit, but let's double check because we want to approach it from the left. So let's see what happens. So we want from the left, that means we need values smaller than my 3. So let's start with maybe 1 and 2 and 3. 3 is obviously a 0. If I plug in a 2, that's going to get me a 6 minus a 9. Make the square root of negative 3. That could make sense if we use imaginary numbers, but that doesn't work with our limits, so that's going to be undefined. Well, let's see what happens when we plug in the 1. That's going to be 3 minus 9. Square root of negative 6, that's also undefined. And what we've realized is that anything less than 3 is outside of our domain for this radical, which means that it's always going to be undefined, which means that the limit from the left does not exist. It is undefined. On the other hand, for this next one, we want the limit as x approaches negative 5 from the right. Well, if I plug in my negative 5, obviously I'm going to get that it equals 0. And again, we want to double check that. So let's create our little table. And so we want values bigger than my negative 5 because we're approaching from the right side, right? So we'll start with my negative 5, and then we'll go negative 4, negative 3, negative 2. Obviously, negative 5, we get a 0 we just found. Let's start with our negative 2 now. So if I plug in a negative 2, it's going to be a negative 10 plus 25 inside my radical. So I get the square root of 15. Plug in my negative 3, I get a negative 15 plus 25. or just square root of 10. If I plug in my negative 4, it's going to get negative 20 plus 25 in my radical, or just square root of 5. And I know, obviously, looking at this, that my square root of 15 is bigger than square root of 10, and that that's even bigger than square root of 5, and that all of these are bigger than 0. And so we're decreasing as we get closer and closer to x equals negative 5. It's all approaching 0. So we can happily say that our limit is 0. Next one, we've got the limit as x approaches 0 from the left of 3 over x cubed. Obviously, if we plug in this 0 right here, we're inclined to say the limit does not exist. But because we're approaching from the left, we don't know that because we don't know that the limit from the left doesn't exist. So instead, we want to plug in some values again. So from the left, we're going to go smaller. Let's say negative 3, negative 2, negative 1. Obviously, 0 is undefined. If I plug in my negative 1, however, that's going to be 3 over negative 1, which is just negative 3. If I plug in my negative 2, that's going to be a 3 over, let's see, that'll be a negative 8, which is negative 3/8. And then if I plug in my negative 3, I believe that'll be a negative 3 over 27, or a negative 1/9, I think that is. And what we see here is that we start off really, really small, and as we get closer and closer to our x value of 0, so as we're approaching 0 from the left, our answers get smaller and smaller. We're going, like if I'm looking at my function, as I get closer and closer to 0 here, from the left, I'm going further and further negative. So this tells me that my limit, this function, is approaching negative infinity, which we also might technically write as the limit does not exist, but typically if it's approaching infinity or negative infinity, we like to write that. So in this case, it's going towards negative infinity because obviously negative 3 is less than what the other values were, which were, I think, like negative 3/8 and negative 1/9. So we're just getting smaller and smaller towards infinity. All right, 3 more to go. So now we are dealing with another radical here. So we want to double check our domain. So we are approaching we are approaching 5 from the right side. So first of all, let's make sure that this 5 is within our domain. And if we plug that in, we get this, which is within our domain. Obviously, 0 is within domain. It's only once we get a negative in our radical that it is outside of that domain and undefined. Since we're approaching it from the right, we're only going to be using values bigger than 5, which means that we should be staying in the domain the entire time. So let's go ahead and plug in some values and see. So if we plug in this 5, we're going to get a 0 plus a 25. So if we create our table again, got our x, y, I've got 5, and that's going to be 25. Let's get some bigger values. We get a 6, 7, and 8. If I plug in a 6, it's going to be 36 minus 25. So it's it's 30 plus the square root of 11, because that 5 times 6 is 30. If I plug in my 7, I'm going to get 49 minus 25 plus, it would be 35. So I get 35 plus the square root of 24. And we kind of don't even need to go to 8 to see that as we get further from 5, we're getting bigger. And as we get closer and closer to our x value of 5, we're getting closer and closer to 25. So our limit in this case is 25 from the right, obviously. If we were looking at the overall limit, it does not exist, because in order for a limit to exist, it has to have a limit from the left and the right that are equal. So if I have, say, this function, and I'm looking for the limit at this point, well, from the left side, it's approaching this y value, and from the right side, it's also approaching that y value. So this limit exists. But say I have this function right here. Well, from the left, it's approaching this y value, and from the right, it's approaching this y value. So these limits, so the limit from the right and the limit from the left aren't equal, so this limit altogether does not exist. Sorry, got a little sidetracked. So let's focus on the problem we're on now. So we want the limit of this function as x approaches 2 from the left. Obviously, we've got another radical. So let's see, is that 2 within our domain? It is, because if I plug in that 2, again, I get that square root of 0. But we're approaching it from the left side. So if I were to plug in a number smaller than this 2, so if I plug in, say, a 1, I'm going to get in my radical, I'm going to 1 minus 4, which means I get a negative 3, which is outside of my domain. And I know that the smaller and smaller I go with my x, we're still just outside of this domain, always. The only way that we would stay within this domain is if it is greater than or equal to 2. But since we're approaching it from the left, we can't be looking at those values. We can only look at values less than 2, which means this limit does not exist or is undefined. Either response works. Now, for this very last one, we need to have some memory of our unit circle and our trig functions. So obviously cosecant of x is equal to 1 over sine of x, right? And so we are approaching, we're finding the limit of this function as x approaches pi over 2 from the right. And so the confusing bit about that is that typically when we're approaching from the right, we're approaching from the right side of our graph. But when we're looking at our unit circle, obviously we could be looking at a graph of this, but typically we'll just be doing this in our head. So working with our unit circle, the right is actually where we're decreasing, right? Because this is pi over 2. This is pi, this is 0, this is 3 pi over 2. So approaching it from the right means I'm going to be considering these values all the way around here, not any of these. So instead, we want to think about what values we can consider then. Well, I know that there is, let's see, we've got 3 pi over 4, 2 pi over 3, and 5 pi over 6. So we're going to once again just make a table for ourselves, our x and y in this case. And so we're going to start, let's start big and make our way down. So we've got pi, 5 pi over 6, 3 pi over 4, 2 pi over 3, and then pi over 2. Now we're going to just kind of work our way down to that pi over 2. And so let's start with pi. So we're going to plug a pi into our cosecant, remembering that cosecant is 1 over sine of x. So if I plug in a pi, that's going to be 1 over sine of pi, and sine of pi it is 0, right? Because our y value here is 0, our y coordinate. So I know that this is going to be undefined. Doesn't help us much, does it? And for our sake, I'm just going to write out our coordinates really quickly here, just so we don't lose them. Okay, that should be, and then, one moment. Okay, so those are our coordinates, and remember, we're always going to be focusing on our y value because it's 1 over sine, and our sine is always our y value, so we're going to focus on those. So then when we're looking at our 5 pi over 6, it's going to be 1 over 1/2, which I can rewrite as 1 times 2 over 1, because I'm dividing by a fraction, or just 2, right? So that's going to be 2. Let's try the next one. We've got 1 over square root of 2 over 2, which just flips our fraction kind of on its head, right? So that's just going to be 2 over the square root of 2. We want to rationalize that, so we're going to do that. Which then those cancel. That's just square root of 2. Let's continue. Oops, I didn't mean to erase that. Oh, I know it. Okay, I'll just rewrite it. I don't know why it keeps doing that. So remember, cosecant x is 1 over sine. All right, now we want to plug in that 2 pi over 3, where our y value is square root of 3 over 2. So it's going to be 1 over square root of 3 over 2, or just flipping our fraction, so 2 over square root of 3, which we want to rationalize per usual, which is this. And then if we plug in that pi over 2, obviously that's going to be 0, comma 1, so it's just 1 over 1, or 1. And so we just kind of see that it is approaching 1, like as we get closer. Oh my goodness. Oh my goodness, why is it? Goodness. So it's just all the way approaching 1. All right, and I think that is all of them. I know a lot of this was pretty confusing, and I know I kind of stumbled upon my words a little bit. But remember, once again, Khan Academy and Google are your friend, as are your actual friends. If they're taking calculus, you can always ask them for help as well. And yeah, I hope everyone got something out of this.